All right, so in this video, we're going to talk about the basic concept of dimensionless numbers. All right, so um, dimensionless numbers are really very useful in fluid mechanics, and we're going to study how to create them, what they are, and all sorts of things. And then we're going to use them again and again for the rest of the semester. So they're a really important concept to handle. All right. So the question is, what is a dimensionless number? So let's start with a dimensional number, a number that you're aware of. So let's say we're talking about force. We've talked about force a lot in this class. We talked about surface tension and forces on curved planes and things like that. So force is a number, right? And it has units of newtons, right? So if I say something is got a force of 10 newtons, right, um, in non-British units, right, kilograms meter second, SI units. All right, that's a dimensional number. We could say pressure, right, and that's dimensional is pascals, which is equivalent to, right, newtons per meter squared. All right. So these are all dimensional numbers. A dimensionless number is when you take a combination of things, of dimensional numbers, and you get a resultant value that has no dimension. So the easiest example is, let's say you were talking about the height of buildings and you wanted to say, what's the tallest building? And you'd say, so you look it up and you say the tallest building had a height that was L tallest. I don't know what the tallest, it's probably the Burj Khalifa right now, a couple of thousand meters, right? And then you said, well, I'm interested in how all the other buildings compare in their height, but I don't really want to know the exact values. I'm just interested in the comparison. So you might say, I'm going to create a new number that I'm just going to call, in this case, I'll call it H, and I'm going to say that's the height of any other building over the height of my tallest reference building. If I look at this number, it has units of meters over meters. Okay, which means it has units of nothing. There are no units in the end, right? So H over here, this value here, this is now a dimensionless number. So let's say I compare the Empire State Building, all right, a couple of buildings. Let's say I say H of the Empire State, H of the Eiffel Tower. And these are not real values. I actually don't know what the answers are. Okay, I'm just making stuff up at this point. H of, I don't know, let's say the Freedom Tower. All right, and you calculate those, right? So for all of these, you get L of the Empire State over L tallest, right? And L of the Eiffel Tower over L tallest, right? And L of the Freedom Tower over L tallest. And you get values, right? Now all of these values are going to be less than 1 because the smallest number is on the tallest building is on the bottom. So maybe the Empire State is like 0.5, and the Eiffel Tower is only 0.1, and the Freedom Tower is like 0.7 or something, right? All right. These numbers, all of these numbers, the H values for these various buildings are all dimensionless, right? Because I've divided meters by meters. So a dimensionless number, and this is a very simple example, right? But in general, this is what a dimensionless number is. A dimensionless number is a number where you've combined dimensional values, heights, lengths, forces, times, densities, material properties, whatever. You've combined those numbers, all right? And the resultant numbers that you get have no dimension, but are still telling you an important thing. In this case, H tells us how tall the buildings are relative to the tallest building. Okay, so why might I do this? Okay. So there are a couple of reasons why we might do this, and we're going to learn about them as we go forward, all right? And how do I do this, right? So there's sort of two questions. How and why, right? So let's talk about why first. 1, dimensionless numbers are really good if you don't know anything about a problem. So let's say the most famous dimensionless number in all fluid mechanics is something called the Reynolds number. And it is rho v d over mu. We'll talk about what all this means, but rho is density, v is the velocity of an object or the flow, d is a length scale relevant to the flow you're talking about, and mu is the viscosity of the fluid around it. So the Reynolds number is the ratio of inertial forces to viscous forces. You wouldn't know that just by looking at it, but it is, all right, and you'll learn how to understand that better. All right, and you can use it to calculate lots of things. So let's say, one thing you could say is, what is the Reynolds number of a swimming fish? And you could say, all right, well, let's say a tadpole. You say, well, a tadpole goes at such and such speed, it's swimming in water, so I know rho, right? I know could use rho of water, mu of water, v is the speed the tadpole swims, d is, say, like the length of the tadpole in this case, and it has a Reynolds number of approximately 1 to 10, okay? That's pretty small. Let's say you look at a really teeny, like a zebrafish. Let's do this. Let's start with the zebrafish. Let's say you look at a bacteria. A bacteria swimming has a Reynolds number of like 0.01, real small. Then let's say you look at like a little zebrafish, a teeny little fish you see in the ocean, maybe zebrafish, maybe that's around 1. All right, then you look at, say, a shrimp. We'll leave out the tadpole. I don't like him anymore. A shrimp is maybe 10. All right, and then you go, well, let's see, maybe like a clownfish, or like a squid, or a small squid like a calamari, or like a clownfish. All right, let's do a clownfish. It has a Reynolds number, let's say, of, I don't know, maybe 1,000, 100 to 1,000. Okay, and then now you're getting big, so you're going to say things like, a tuna, a bluefin tuna, they have Reynolds numbers on the order of like 10,000. All right, and a whale, all right, they might have Reynolds numbers on the order of 100,000. All right, so when you look at these Reynolds numbers, right, you can automatically start to see, well, clearly the way a bacteria swims is probably different than a way a whale swims, just by evaluating the Reynolds number. Now, I don't know anything about the physics, but I can tell you that, listen, I know this Reynolds number exists, and by looking at these values, they're clearly different. Let's say you study a new fish and you say, I have this new fish, I've never seen it before, and I calculate its Reynolds number, and the Reynolds number of my new fish is approximately 10 to 100. All right? What is that going to tell you? That's going to tell you the new fish is somewhere in here, right? So it probably swims something like, in terms of the physics, like a shrimp. You need not know what the physics are, but that is an answer. All right? So one reason we care about the Reynolds numbers, if I don't know anything about dimensionless numbers, if I don't know anything about a problem and I calculate the dimensionless number, it gives me insight into the problem. Okay? So that's a really important thing. When I don't know the physics of a problem, the Reynolds number can give me the dimensionless parameters can give me insight. All right. The other really important thing about dimensionless numbers is they reduce variables. So again, we're going to go to the Reynolds number. It's not the only number that matters, but Reynolds number again, rho v d over mu. Look, the Reynolds number takes 1, 2, 3, 4 variables and makes them into one thing, right? So now let's say I'm doing a study and I want to know and I know Reynolds number is important to swimming, we've already decided, and I'm going to say, I want to know how fast something swims, or how much energy it takes for something to swim. So energy is force times distance, right? So let's say I have a way to calculate the force of a swimming fish, all right? And I say, okay, so let's look at the energy of swimming as a function of, well, I could do it as a function of rho. That might be good, but that's probably not important. Maybe it is, I don't know. I could do it as a function of v, all right? I could do it as a function of d. Oh, I could do it as a function of mu, right? I could do it as a function of any of those, or I could do it as a function of Reynolds number, right? And I'd get some sort of curve. It doesn't matter what, right? And now, why does that matter? Well, how do I change Reynolds number? I say, well, let's say I do Reynolds number and I say I do several Ds. I do D1, D2. So I look at several different size fish, D3, D4. And for each one of those, I get a Reynolds number 1, Reynolds number 2, right? Reynolds number 3, Reynolds number 4. All right. I changed diameter to look at that, but let's say I did a little thought experiment. I said, well, I could take a fish of the same diameter, but I could change its velocity. So let's say same V. And I could change its velocity, right? And I could get the same Reynolds numbers, right? Which means in order to test the effects of velocity, density, viscosity, and length, all I actually have to do is go through one set of Reynolds numbers, okay? Assuming the Reynolds number is the important thing. So rather than having to make 4 different curves and look at 4 different variables, I only need to look at one variable, Reynolds number, and I can figure out a way to change that either with velocity or viscosity or diameter or density. And that gives me a way to look at the problem, and then I can always figure out how that relates back to the parameter I cared about. So dimensionless parameters reduce the number of variables I have to care about. All right, and finally, all right, they give us an insight into physics. So even though we don't need to know physics to understand the dimensionless parameter, again, if we know the Reynolds number of 2 situations is similar, we can infer the physics are similar. And if we know that the Reynolds number is roughly inertia over viscosity or over viscous forces, then we can say that like a Reynolds number that's really big is inertial dominated. And a Reynolds number is really small is viscous dominated. All right. So it allows us to simplify problem and give us insight into the physics. Even without knowing what the equations are that govern the problem, we can have a guess as to why that problem is important. And we can use that to understand the problem better and hopefully find the right equations to study. All right. So these are really the 3 reasons we care about the dimensionless parameters. Okay.